Hello, this video is on section 8.3, which is titled Rational Functions and Their Graphs. And there are two learning targets for this one. The first one is to identify properties of rational functions, and the second one is to graph rational functions. So let's go and get started. A rational function is anything that looks like p of x over q of x as long as those two things are both polynomial functions. So more specifically or simplistically, you basically just have a fraction where you have a polynomial on top and a polynomial on bottom. It doesn't have to be quadratic. It could just be x plus 1, it could be x cubed, x to the fourth, it could be anything like that. As long as it is a fraction where polynomials are both on top and the bottom. And so the domain for this rational function is all real numbers except for when your denominator is equal to 0. And in 8.2, when we were talking about asymptotes and we were making our domains as something that looked like negative infinity to 0 and then 0 to infinity. Another way you could write this domain is to just say all real numbers except 0. So the domain on this graph that goes from negative infinity to 0 then starts back up at 0 to infinity is the same thing as all real numbers except for 0. Those are the two exact same ways to write the domain, just a little bit differently. One may be easier for you than the other, just kind of depends. And then when we're looking at these rational functions, there's two different types that they could be. The rational function could be continuous, where all the way through the graph it does not stop, it doesn't move, anything like that. And the way you can determine if it's continuous is that if your denominator can never equal to 0. So for example, if our denominator was x squared plus 1, then it would never equal 0. No matter what value you plug in for x, it can't be 0. And then it's discontinuous if at any point your denominator can be 0. So this example I have up here, where the denominator is x squared minus 1, this can be equal to 0. You set it equal to 0, solve for it, and that number is where it is discontinuous. And the two different types of discontinuities that we're going to focus on is the first one is a removable discontinuity, or what I like to call as a hole. So it's a big old hole in the graph or in the line where you're drawing it and there's an open circle. So at this point in the graph, it does not exist. There is no point on there. It is discontinuous. Then the other type is a non-removable discontinuity, which we talked about yesterday. A perfect example is an asymptote. We can't remove it from the graph. It doesn't connect up at all in the same spot. There is an asymptote that is separating the two. So again, it can either be continuous, discontinuous, and the two types of discontinuities are either removable or non-removable, which is either a hole or an asymptote. And the other thing I want to talk about is finding asymptotes within the equation of our graph. So the two different types of asymptotes we have is it could be vertical or horizontal. If you have a vertical asymptote, that means your denominator, remember q of x is our denominator, has a 0 that does not cancel with our numerator. So in some instances, you'll be able to factor out the denominator and numerator. If they can cancel out, then it is not a vertical asymptote. But if your denominator doesn't cancel out with anything, whenever that is equal to 0, it's going to be a vertical asymptote. And we'll do some examples in class that show more specifically and a bit easier on how we can do that. And the other one is horizontal asymptote. And a horizontal asymptote looks at the degree or the power, whether it's squared, cubed to the fourth, of both the numerator and the denominator. So if we look back at our example on the first one, where it was x squared plus 1 over x squared minus 1, the degree of the numerator is 2, and the degree of the denominator is 2, because it's the highest term, and those are both the degrees on there. So if the degree on your numerator is less than the degree on your denominator, that means you have a horizontal asymptote of y equals 0. If the degree on the numerator is bigger than the one on the bottom, then you have no horizontal asymptotes. And if the two degrees are the same, which we have in this case, where the both degrees are 2, then what your asymptote actually is y equals a over b, which is the coefficients of the highest degree terms. So the coefficient of your highest degree term for this one is a 1, and the coefficient of this one is a 1. The coefficient is the number in front. Number in front of term. So our horizontal asymptote takes these two numbers and divides them. Y equals 1 over 1, which is the same thing as y equals 1. So the horizontal asymptote for this example would be y equals 1. I know this video is a lot, and we're going to be doing a ton of examples in class today. So just kind of be prepared. Make sure you're taking a lot of notes, especially over the horizontal section, and then back to the removable and non-removable different types of continuous and discontinuous types of graphs. Okay, thank you.